Okay, so welcome all. So today we will be looking on a column design, the steps involved in column design. It will be mainly a rectangular column axially loaded. Okay, so let's see. It is a axially loaded column. Okay, a rectangular column. Okay, so the step one will be, let's see the step one. Identification of the short column. Okay, uh, for short column, for short column, the L effective divided by LLD should be less than 12. Okay, so the L effective is the this is the length responsible for the deflection. Okay, if this is a column, if this is a column fixed at both ends, so if this is the deflected shape, so this is the L effective, the total is the L effective. Okay, so the L effective is mainly defined as the length that is responsible for the deflection. The LLD is the least lateral dimension, least lateral dimension, mainly that is the smallest dimension is the least lateral dimension. Okay, so when we will do the numericals of this, so it will be clear in that step. Okay, the step 2 is we have to take out the minimum eccentricity. Okay, so the minimum eccentricity. Okay, so let's see how we will calculate the minimum eccentricity. So the E minimum is calculated as the unsupported length divided by 500 plus least lateral dimension divided by 30 or 20 mm, whichever is maximum. Okay, so the unsupported length can be written as L naught also. Okay, so this is the A minimum formula. We have to do the unsupported length divided by 500 plus the least lateral dimension. This unsupported length can be also the L effective value. Okay, plus the LLD least lateral dimension divided by 30 or 20 mm, whichever is, or you can write it here, or 20 mm, whichever is maximum in this. Okay, so here one thing is there, that is, let's draw a column. Okay, so this is the cross section of a column. Okay, this is the cross section of a column. Okay, so this is the cross section of a column. Okay, so let's see, this is the x direction and this is the y direction. Okay, now let's say this is D and this is B, this dimension is B and this dimension is D. Okay, so when we will find out the E minimum for a rectangular column, we have to find out in both the direction. We will find out E minimum for both the direction. Both the direction. That is E minimum for x direction and E minimum for y direction. Okay. So see the L effective, this L effective or L naught value, this unsupported length value is same for both the direction, but this LLD, least lateral dimension, will change. How it will change? Let's see. See, one simple thing you have to remember it, that is when LLD, when we are finding out E minimum in x direction, see the x direction is cutting which dimension? It is cutting the D dimension. Okay, so when we will find out the E minimum in x direction, in that case the LLD value we will take it as this D. Okay, for direction x we will, the line, the x direction which is cutting the dimension, we will take this. It is cutting the D dimension. And E minimum for y direction, so the LLD will be, is very easy, B, as because the y direction is cutting the dimension in B. Okay, so this both the dimension, both the direction, E minimum, eccentricity minimum will be calculated. Okay, now we have to check one thing. See, E minimum we have calculated, but there is a clause of checking the E minimum. If this clause is valid, then only we will consider eccentricity value, or else we will not consider. So check for eccentricity. Check for eccentricity. Okay. So what is the check? Let's see. For x direction, we are taking, see, first the formula is E minimum should be less than or equal to 0.05 LLD. Okay, so for x direction, what we will get? E minimum for x direction should be less than or equal to 0.05 D. So LLD is D in x direction, and for y direction, okay, so E minimum in y direction should be less than or equal to 0.05 B. Okay, so we have got it. If this value is justified, this E minimum value that we will get from here, and we will calculate it 0.05 D and 0.05 B. If this value is less than that, then only we will consider the eccentricity value. Hence, if this condition satisfied, then only, then minimum eccentricity value is taken in effect. Okay, taken in effect. Okay, so now we will see the load carrying formula. Okay, so the step 3 will be the load carrying capacity. The load carrying capacity formula. Okay, that is represented as PU. Okay, see here, PU is equal to 0.4 FCK AC plus 0.67 FYAS. Okay, so mainly we have to calculate the AS. Okay, so if we see main aim is to calculate the AS, area of steel. Okay, so here FCK we know, Fy we know, AC is area of concrete. AC is area of concrete. Okay, so see one thing, area of concrete we don't know, so how we will calculate? So let's say AG is the gross area. Okay, so AG is the gross area. So what is the gross area? So gross area is B into D. The gross cross section area will be B into D. Okay, for a rectangular column, for a rectangular cross section. Okay, so now what is AG? AG is equal to AC plus AS. The total gross area will be the area of the concrete plus the area of the steel. Okay, so from here we can take it that area of the concrete will be AG minus AS, the gross area minus the area of steel. We will get the area of concrete. Okay, but this formula, see, one thing we have to see that this formula we are getting, okay, well and good, but but one thing, that is, this is for the short column. For short column, okay, when we will find the load capacity for long column, for long column, load carrying capacity, okay, load carrying capacity, how we will derive? See, as per IS 456, we have got a reduction factor, a reduction factor, okay, that we represent it as CR. This is only for when we will design for long column. Okay, that is, the reduction factor is 1.25 minus L effective divided by 48B. Okay, so what the formula will be? You have to just multiply this reduction factor with the formula. So hence, what's the formula? The load carrying capacity formula. Okay, so the load carrying capacity formula comes to CR into, it will be as it is. Okay, the previous one, it will be same, only the reduction factor will come into action for long column. Okay, now let's see. Now we have to calculate the area of the steel. Okay, so from this formula, for long column this, and for short column this, the area of steel will be calculated. Now what we have to do? Now step 4 is, you have to find out the number of bar. Okay, so AS is calculated. Now we have to do, now assume dia of bar, and thus find out number of bars. Okay, number of bars. So how we will find out? N is equal to number of bars is the total area of steel divided by 1 area of steel. Okay, here phi is the dia of 1 bar. Okay, so now we will see the next step. We have calculated the main bar. Now we have to calculate the transverse reinforcement, the lateral ties or the stirrup or ring, or whichever language you will tell. Okay, so it will be the step 5. So transverse reinforcement, transverse reinforcement. Okay, so the main reinforcement is calculated. So this is the main reinforcement. Okay, so the transverse reinforcement will see here, according to IS 456, the dia, according to IS 456, the dia of the transverse reinforcement will be phi main divided by 4 or 6 mm. Okay, whichever is maximum. Okay, so in this way the lateral ties dia will be fixed. Okay, now let's see the next step. Okay, step 6. So step 6 is the spacing of transverse reinforcement or lateral ties, which whatever you can tell. Okay, so according to IS 456, it is given that the spacing will be LLD or 16 times the dia of the main bar or 300 mm, whichever is minimum. Okay, so the spacing is now calculated. Okay, so one step is left, that is you have to calculate we have to check for the minimum and the maximum reinforcement of the main bar. Okay, so the step 7 will be step 7, that is check for minimum and maximum reinforcement. Okay, so what is the check? Let's see. The check is the area of steel should be greater than 0.8, okay, greater than or equal to 0.8% of cross section area. Okay, and the area of steel should not be greater than 6% of the cross section area. Okay, so this is the check, and the last step is we have to do the detailing of the column reinforcement. Okay, detailing, detailing of column reinforcement. Okay, so last step we will do detailing of the column reinforcement. How we will do? Just we will see one thing. We have to draw a column like this. Okay, we will draw a cross section of a column like this. Now we will draw the main reinforcement like this. Okay, if say we have more number of bars. Okay, and now we have to also show the lateral ties. Okay, we'll also just show our lateral ties. Okay, so this should be the detailing. We have to tell the dia of the main bar, the dia of the stirrups, and also the spacing. Okay, dia of the transverse reinforcement, the dia of the main bar. So in this way we will just conclude it. In the next lecture we will start with a numerical. Okay, thank you.